Good afternoon. This is our last presentation for today. I'm closing the plenary part of our conference, and I'd like to use this time to tell you about the existing capacities of radar data processing based on the images acquired in the mode of interferometry. Generally speaking, having an interferometric series, one can get significantly larger volume of information compared to processing of singular images of interferometry pairs. A couple of words about what is interferometric series. These are the images acquired in orbits located about hundreds of meters or up to 1.5 kilometers apart from each other. They can be acquired with a single orbit of one spacecraft in some time. I'm not talking about tandem work here. It is called revisit time in English. So for such modern systems like Racurs is 9 days. For Skynet satellite constellation under 1 day. In about 1 month, one can acquire from dozens up to dozens of images. So what is an interferometry image? We can get also phasal information from it. Phasal information can be used for generation of digital elevation models and for detection of subsidence up to fractions of millimeters. It depends on the noise phases on the interferometry. Here you can see different interferometric series applications. It would be interferometric DEM generation, millimeter accuracy amplitude change detection, surface classification, interferometry with the constant reflectors. There are also such methods. Then change detection with the phasal method, incoherent processing accumulation, then change detection for radar amplitude, surface classification, and polarimetric data processing. Now a few words about each one of these methods. Digital elevation model generation. What is the difference if we have a series of interferometric images, say a couple dozen, 3 dozen, the simplest thing that we can suggest, and what works well actually, is the selection of the pair which would match best in terms of coherence between the images. Coherence in that respect would be correlation between two images. This is not amplitude but rather phase-based correlation. How does it work? I will show you an example of the interferometric process which is included into our software suite PhotoMod Radar D. You can find additional information on the Racurs site in the product tab. There is such function as normal interferometry, that would be rectification of the digital elevation models. Now, the flow chart of digital elevation model generation includes a number of operations. First, image pair co-registration, as we call it, then interferogram formation, phase filtering, phase unwrapping. In other words, we're turning the phase from conditional from 1 to 0p to absolute, then phase to height conversion, and then comes geocoding of the acquired geomatrix and the generation of digital elevation model. So this is a simple example now. 2 images acquired by RadarSat-2 So these are the test images that they uploaded for in open source. You see two images here. To your left, on the left picture, you can see different phases, and on the right you can see coherence, which shows the level of correlation, phase correlation between images. The blue color shows low coherence, the red color shows high coherence. Thus, having a whole series of images, we can simply select the pair, which we can process based on the level of coherence. So the higher the coherence, the more will be the accuracy of the generated digital elevation model. Here you can see ultra-rectified radar image, geocoding based on the altitude, and the altitude was acquired just like Baron Munchausen drew himself out of the water by his forelock. That was a fairy tale, and here it is not. And the generated digital elevation model here is a octa-rectified matrix. The next type of application, again, if we have a sequence of interferometry images and we need to build a digital elevation model, we can use a simple method here by building for each digital elevation model first and then have an average result. What can it deliver? We have the so-called phase noise, because the images acquired by radar is an active sensor. It has a transmitter and receiver, and receiver on the output has phase detector, but it generates noise, and this phase noise can deliver some altitude errors. So to approximate these errors, we can get a number of pairs and get the required result. Here you can see the sequence of images from radar images for a section of land in Novi Uringui. It was acquired by Terasar X. You see how different these images are depending on the time of acquisition, and here you can see their interferograms. You see the quality of interferograms and phase pictures are different. In some places they're good, in others they're very bad, which means that we can always select the better ones and then we can approximate them. An approximation can be done not simply like this, but via coherence, by selecting only those places where coherence is high. Here you can see how coherence masks can be used. There is such a possibility for interferometry. We can build masks and use them when deploying or unwrapping the phase. Now moving on to the next stage, which is interferometric series processing and DIN-STAR processing. Here again first stage is coherent co-registration of all images from this series. Then we identify based on 2 or 3 images the displacement extraction. Then we identify temporal changes that happen in the gaps between the images. This technology is ensured by the interferometric process, which has an option of differential interferometry, 2-pass mode, 3 and 4-pass modes. Here you can see the stages of processing with a 2-pass mode. To your left you can see 2 interferograms acquired with the use of a digital elevation model, and as an output you get the result of subsidence of the surface. Same thing can be done with the use of 3 images. That will be 3-pass differential interferometry, and 4-pass also possible. Here you can see different stages of processing. We take 2 images, prepare an interferometric processing. We have differences in phase, and then there calculated one from another, and we have differential interferogram showing the subsidence. Here on the picture you can see a volcano with the movement of, it is not lava, it is glacier, but it is melting a bit, and you see the light and dark parts, and there's movements in different directions. That's why it is dark and light. Another technology of differential interferometry, the so-called permanent scatterers technique. It is a very fashionable thing at the moment, trendy, and for that we need dozens of images, but sometimes it's usually about starting from 50 images would be sufficient. It depends on the efficiency of the technology. Now we're in the situation when this process is only under development. We have prepared a maquette, and now we continue working in this direction to make sure that this technology is then later implemented in real life. This technology foresees a number of stages related to the choice of permanent scatterers. So these are the elements which can be clearly identified on all images, which from image to an image have the same phase of scattering. Then we build a grid, we calculate a vector for each point, and as a result we can acquire a set of points which would characterize the subsidence of surface for these permanent scatters. Now we shall talk about change detection on the surface using the phase method. Again, here we can use coherent co-registration based on the phase. Then we do the phase extraction and coherence extraction as well. For that we prepared a special software. This is a surface change detection using phase method, and again it has a sequence of operations. First, high precision cogeneration, coherence estimation, phase filtering, phase changes detection, geocoding of output matrix, then improvement and vectorization. Next option of interferometry series processing is incoherent processing or incoherent accumulation. But again we start with a coherent co-registration with a phase. Why do we always have to do this? The main idea is that unlike if we combine images based on amplitudes, the accuracy in the best case would be only half of the resolution. But if we combine them based on the phase, then the precision of the matching would be a 10th or even a 100th part of a pixel. And that is why when after co-registration we start matching the images, we do not lose the spatial resolution. And by combining them, we one way or another reduce the noise which exists on all radar images. The so-called spectral noise, which can be of course subdued by some filtering, but it will reduce the overall resolution. But we can do it differently. Here is an example of processing in the same sequence. We use 33 images for that from Terasar X for the same section of interferometry series. Here on the top left image there's a single image. This is what an urbanized surface looks like, and on the single image, and after such processing of accumulation, you see the level of noise has greatly changed. And some other examples, here you can see an example of railroad. On the left top image it is a single image. It's hard to detect how many lines of road they have there, but after such accumulation you can easily calculate the number of rails. This is the comparison of the acquired radar product with the optical image. high-resolution optical image. Here, same operation was done for a bridge over the river, and again, the level of information has greatly increased. Same thing was done for standard 5-story buildings, and some of the 5-story buildings we can even count the number of and position of ventilation shafts. How can it come in handy? Of course, it's not so good as the modern optical images, but here you need to take into consideration one important thing. In some of the areas, especially for our country, it is of special relevance. We can fail to get any optical images for months or even years in a row. There are some areas in Russia. And here we still get some information and can prepare some maps based on these data. Here you see a similar situation with vegetation. On the right image below, you can see separately standing trees, even their shadows. So this is the advantage of such processing. Such processing is implemented by the software product, which is included into the into the software suite of radar complex, and you can see the processing coherent images. You can learn more about it later on. Moving on, change detection based on amplitude. Extraction from radar images. Again, we do matching, and then using same product, by interpreting or converting different images into red, green, and blue bands, we can see images showing the changes that happened in the period between when those images were acquired. Surface classification can be done by the same software suite that we are referring to. This is yet another product which was acquired after a coherent matching of the series of images. And then the use of polarimetric data, we can acquire not only in one polarization. The modern radars make it possible to work in two polarizations. On more advanced ones, like RadarSat 2, can ensure a full polarization matrix. What can it deliver us? Here you can see two images. This is a section of the beach area of Hainan, where we are at the moment. This is our hotel area. And this is an image acquired with the horizontal polarization and the vertical polarization. The images are quite scaly, so you cannot see real differences, but there are differences there. If we prepare an interferometry processing for this and get the coherence for horizontal and vertical polarization, you will see that some of the changes are here. They're explained by the fact that there are different objects that differently react to the polarization of falling wave, and as a result the changes happening in time for vertical and horizontal polarization will also be different. Here you can see it. These are the differences between the interferometry pairs of vertical and horizontal polarization, and we see that the biggest change, biggest sensitivity was acquired in the area of whether water or some artificial objects. If all this acquired data are positioned into different color bands, then we can more accurately classify the surface. Yes, we can easily classify artificial objects that behave differently. And just a couple of words about the improvements in the software suite of radar. And as long as we had a process of geocoding, which allowed us to geocode radar images, what was added? we added the possibility of automatic matching with digital elevation model, so we don't need to look for a digital elevation model anymore. If we have SRTM 90 and SRTM 30, then the search for a required digital matrix and generation are done automatically here in the interface. It is enough to put a tick on the project, not only SRTM 30 and SRTM 90, and then the program will do everything itself. This is the octa-rectified image for such coastal area of Hainan. You can see two places. You can see them from the windows of the hotel. The hotel is placed here, and automatically they generate the altitude matrix which was used for processing of this image. Then this ortho-rectified image can be superimposed on the optical image to compare the accuracy, and for that now we do prepared an additional product, again new trendy thing. It was mentioned a number of times. This is 3D modeling, and here you see automatic uploading the ortho-rectified image, which is then matched in online mode from different servers. You can select the optical data. Here you can see how this works. So far it is still a prototype, it's still under development, and these are the screenshots of this is a radar image to your left, and to your right is the optical image. You can select the source from where we are going to acquire this data, and various options of processing related to transparency. That's it. Thank you. Thank you, Igor. Are there any questions for Mr. Elizavetin? Okay, thank you. Then